class. He was coming to a conference in Chile, so he contacted me offering he can come visit us, and it was great. So that's why we have him here for the seminar, and also today we have a meeting with media and the people from the International Fair Office, also to explore some possible Erasmus Plus contract, so that's something good for all of us. I will give the floor to Santi that he will present him properly.
We'll present you in Spanish because it's faster for me.
Please. I don't understand anything anyway. Sorry.
You have to believe me.
I may pick up one or the other word.
Bueno, el profesor Weigand es un destacado científico especializado en química inorgánica molecular, con enfoque en metodologías sostenibles, aplicaciones técnicas y estrategias de reciclaje. Se formó en la LMU de Múnich, donde obtuvo su doctorado en 2005 con distinción y recibió el premio de Cultura de Baviera ese mismo año. Tras una estancia postdoctoral en Canadá con una beca Leinen, continuó su carrera en Alemania con la habilitación en Münster y la beca Liebig de la FCI. En 2010 fue seleccionado por el programa Emmy-Noether de la DFG y recibió el premio Waller para jóvenes científicos. 2 años más tarde obtuvo una RC Starting Grant y desde 2013 es profesor en la Universidad Técnica de Dresden. Más recientemente, en 2023, obtuvo la financiación Reinhard Holzberger de la DFG para su proyecto Blueprint for Modern Sustainable Phosphorus Chemistry, que se incorporó en la CTC Expert Pool. A lo largo de su carrera ha publicado más de 150 artículos y su trayectoria refleja un compromiso sostenido con la innovación y sostenibilidad en química de la industria. Thank you very much, Jan.
Thanks you for the kind introduction. First of all, thank you that it worked out, and finally the first time in South America, and I really like it, even if I had a small incident in Rio, but well, I've been told that's normal in Rio. I sent a few abstracts and topics, and so in the end we decided to put everything together. So whenever it's too long, I'm just going to interrupt me and I'm going to stop. So first of all, thank you. I could pick up some of the words, and unfortunately not fluent in Spanish at all. I'm just going to say some good evening, good morning, and so on and so forth. But it may improve if we're going to continue to work together with South America, and well, particularly also trying to get these Erasmus Plus. And so for the students out here in the audience, I really recommend you to see the world and try to get those opportunities, hopefully, that are coming up, in order to explore also other opportunities. And I show you some of the work we've doing in my group. I'm not only doing research a lot, we are also doing a lot of startups nowadays, and that's also some motivation I'd like to give, particularly for students in the moment. So the research, first of all, of course, I have to say thank some of the organizations that actually fund us over the time, and more and more nowadays, and you also know this, funding situation is a huge problem. Not only here in Argentina, I realize this is a massive problem, but also in Germany it starts to become quite tricky, particularly also to fund fundamental research. So fundamental research, which is, I think, in my opinion, the most important one, because it's the basic of everything. We had the discussion this morning. Chemistry is the basic of everything, and so we have to coin the words also to make students and people understand that without chemistry there's nothing. 99% of all the products goes to a chemical process, and that's not being made aware to most of the people. So what we also do nowadays, we're going to go right to industry funding, and so trying to use our fundamental research from main group chemistry and trying to do it into application. And so I have at the end, if we have enough time, an example for something like this, which was introduced about the blueprint of phosphorus chemistry, where we're looking into making more sustainable, greener processes. I don't like the frame or the coin green chemistry. I'm not a plant, but greener chemistry are aspects where you find hotspots that are problematic in chemical processes, and so with some adjustments and modification, you can make processes indeed more sustainable, economically benign, and so on and so forth. And this is what we're trying to do. And particularly one element is very important in that regard is phosphorus, as it is really something that is particular in Europe from a point of supply a problem. When we talk about the elemental phosphorus P4, because we don't produce it. So whenever the geopolitics will change and we see that everything is a little bit in a rumor, We never know, so if certain supply chains are going to be ceased, we have a massive problem. And so this is what we are addressing. I will show you something at the end. But of course we start with something completely different, and this is on the next slide. I joined TOPO in 2015. Now you may ask why I'm showing something like this. We had to redo a chemical, like an industrial chemistry practical course, and together with my colleague from the food chemistry, we decided to modernize our industrial chemistry. So we had in the curriculum something it's called biotechnology processes, and used to be wastewater treatment. And I'm not a big fan of wastewater treatment because in the lab the smell and everything. So we decided, both are coming from Bavaria, so my colleague Thomas Henl is also Bavarian, which I am also, or more precisely Franconian. But anyway, for both aspects, for food chemistry and for the industrial chemistry, we decided to put a brewery unit, a brew unit in our course. So students learn now how to make beer. That looks maybe quite funny, and I took some slides out because we have not too much time, but what I'd like to show you, from this brewing unit, making alcohol and fermentation broth, the next stage, what then we've done, is we implemented also a distillery, or I implemented a distillery, so in order to separate alcohol, and so some projects we are related to is converting ethanol in biofuels, for example, and using like natural fermentation processes to do that. You not only can make ethanol to do a biofuel, you can also make gin out of it, but that's something which we of course do on pleasure as well. So why that sounds of course funny, but what I'd like to show you is you can generate IP, you can generate even a company, and so we started that up and we built our own brewery. So that's something what particular students, if you generate IP, it is your IP, it's not your boss. You can generate it together with your boss, and then you can find maybe people in crime who are going to make it happen. So try to apply it, because even if you have a paper, or you have a textbook or something like this, it's just paper. Maybe people read it or not, but only the application later on is going to do something. So whenever you generate IP, do not lose it, use it. And so we've done this. So we both started this up. Everything started 2015. And then 2019 we founded the Lawman's Brew, and that has become even a bit bigger. So we built our own brewery now. You see here the units, how it looked like from the first sketch. Here's are the fermentation tanks when they brought down to the cellar for the production. And there's a small movie. This is Thomas. This is me last year, a bit bigger. I lost a bit. Now you know what I was talking before. So this is our brewery in the university. And then of course we put it over into a tap room. This was the first tap room. Now we have 25 people, and that of course gives a lot of responsibility because we have families, and so you work double so hard in order to make it happen. Yeah. And I saw this also now the last days, that there are so many small companies, people trying to make something out of what they create, and I think this is really something where everybody can contribute. So whenever you have an idea, even out of chemistry, there's a lot of application which is really important to be applied. So I took some slides out because from the beer brewing you can make fermentation broth, and you can also make spent brewer's grain, which is the remainings. And we, for example, use the spent grain from the production as a bioabsorbent in order to use this for the decontamination of radioactive waste, for example. It works quite fine. But that's a different story. I was asked to really focus a little bit on, yes, more like separation, lithium recycling, and we go from lithium recycling, send a bit to molecular, to completely different topic to silver clusters, and in the end a bit of phosphorus sustainability to come back. Okay, so as I said, we'd like in our group to really look into recycling. And one of the most pressing problems, and as a molecular chemist, we combine our phosphorus chemistry with other topics. And one of the most important ones, for example, is the lithium recovery. Electromobility, and I'm going to give a bit more of context in a moment, really is depending on, like, for example, lithium iron phosphate, which is a cathode material for normal electromobility. It's the cheapest stuff to make, to be honest, but it's also very easy to recycle. So one process, we just introduced a full recovery in order to take this black material, use leaching and oxidation processes, later crystallize, and then even separate lithium selectivity, and I come back to this in a moment, and we even can recover the phosphoric acid being used in the process. So the whole process actually can be used in the end to resynthesize completely lithium iron phosphate. And so that motivated us over time to not only look into lithium but also look to other aspects. And so we also, it's very easy to blend. Maybe my finger is too strong. You warned me that this is very tricky. So we also looked into a lot of reverse metal recycling, so fluorescence lamps or even from spent catalysts. And what you can do, and what we do in our group, also we print our own reactors in order to, for example, oxidatively separate cerium-3, cerium-4 from lanthanum, for example, by an oxidation process. So what I'm trying to tell you is in our group, we're not only trying to understand the fundamentals, but we also try to synthesize our own new separation extraction kits. Okay, back to lithium a bit more in detail. As I said, the motivation, particularly here in South America, is of course quite important. And I've been in Chile last week, and I tried to visit one of the mines there where you can actually mine lithium, which is a quite complicated process. People don't really are aware how much water you need in order to recover or to mine lithium. And it's a project that takes between 12 and 24 months. And so if you look into this, it's of course much more interesting to look other resources, but primary resources in order to sustain our society and sustain our also infrastructures and to make lithium available. Because, and you know, this motivation, the supply for lithium, the demand for it is going to be rising dramatically because of electromobility. I have my own opinion. I think lithium, LIPS and lithium technology is good for something like this. It's a stupid idea to put it in a car, but that's my personal view. Sodium batteries and something like this are not on the not able nowadays to really substitute most of the lithium one. That would be, of course, much better. So there is a lot of research going on sodium-based solid-state batteries, but that's not there yet. And sulfur batteries needs higher temperature, which is also not the way to go at the moment. So in my opinion, we need to have a mix anyway, out of biofuels, battery technology, and so on and so forth. So we cannot rely on just one technology. In Germany, we did a mistake. We said, okay, don't look into biofuels anymore. 6 years ago, they cut it, only by batteries. And our industry, of course, chemical industry, was completely prepared for that. Not at all. So we're having a problem. What do you think how much lithium is being recycled at the moment? Approximately number. What do you think? Any number? 1%. Thank you, that's exactly what it is. Approximately 1%. And so the European Union says, okay, we have to recycle by 2030 in 30%, for example, something like this. But they didn't say about lithium. They say you have to recycle a battery 30%. So if you look at the case, aluminum or something like this, and lithium as the third lightest element, there's almost nothing in. So when you recycle everything else, you have your recycling rates already. Now they modified that a bit, that they said, oh, you have to recycle lithium. So, but lithium recycling actually is not that easy, yeah? And so we're looking into the two types of ligands you can use for lithium recycling. And so, for example, some ketones, beta-decatones, and HTTA, this fluorinated version. This is something which is in industry for quite some time. It can also be used nowadays for lithium recycling. But you see already the problem, fluorinated compounds, and also that will be a problem in the future. PFAS and everything which is perfluorinated will become distinct from the chemical lists for the future, cannot be used. So we're having already problems that companies closing down and don't produce PFAS anymore, and also everything like this, which is of course also for pharmaceutical application very important in order to surpass patents and in order to make lipophilicity higher, in order to brain barriers and so on and so forth is quite important, but again, when it ends up in the later, you have a problem. And there are also lithium-ion pair receptors, and I maybe have forgotten to mention that lithium and LIPS is normally lithium hexafluorophosphate. So it is good if you have the cation and you recover the anion at the same time. So with those ditopic ligands, you are able to capture lithium together with the anion. I don't talk about this too much. So what we've done, we combine these technologies with pyrazolone. And so pyrazolone, we just implemented a phosphorus in the backbone because I'm a phosphorus chemist. And what it turned out to be that these kind of ligands are quite interesting, not only for lithium recycling, but also for reverse separation. And you know, rare earths is of course a bit of a problem. You have the early and late rare earths. The ionic radio is quite similar, so the differentiation of the different cations is a bit of a problem. So we have normally, when we do our research, we pick a early, that was a light, lanthanum, erythrum, or ytterbium, as an example, and we looked into possible extraction procedures. And so, first of all, a little bit of chemistry, of course. How do you make those phosphoryl pyrazolone? I'm not going to go into much detail. It's very straightforward organic synthesis with a little bit of phosphorus in it. What's maybe more interesting is that we can alter the substitution pattern quite significantly. Why? We have different kind of substituents. R1, which is like on the phosphate or phosphorus moiety, the esters here in the background of the pyrazole, or we can also in the para position. We mainly at the moment looked at the para position because the hydrazine which you use, it's more affordable and straightforward to make, but of course nowadays we're also looking in the ortho and para position, but that's a different topic. Now you get a generation of different kind of ligands depending on the substitution pattern, and then of course you can try and look into coordination chemistry. So it is not only interesting from a point of view that you look in the coordination, but you also can have a look into selectivity. What kind of coordination is it? With 4 or 3 ligands, can you add a co-ligand, and so on and so forth. And so it's a very, very nice coordination chemistry you can look into this. And so depending really on the ionic radio, we can now differentiate. And also, since we have phosphorus in there, we also have a very nice NMR handle, and we also can follow the coordination in solution. So that means we can see really if our ligand is going to be on. And this is an example, even if you have some paramagnetic metals in there, we still can most of the time observe a phosphorus NMR signal, and then we can actually decide or derive some coordination on it. We looked into it, and it turned out that it depends, and you see that the early compared to the late ones, we have a selectivity towards the earth metals. And depending on the substitution pattern, remember we have different kind of substitution, H2 till A15. We also have like stronger selectivity. For example, HL15 has a bit of an ytterbium, or even if you see something like here, HL5, it is really much stronger and it doesn't really go for a europium lanthanum. And so by adjusting the electronic effects, by adjusting the sterics and so on and so forth, we really get selectivity, which is normally quite of a problem. If you think about rare earth metal purification, you need a lot of mixer settler. That's a technology typically being used like football fields long. Now if you are more selective, you can reduce the size, you're more sustainable, you need less solvent, and you have with a better extractant a much better separation factors and purification in order to really have pure rare earth metals in the end. We did not only look into rare earth metals, we also looked into actinides, and so that's something which we are able to do. We still can work in our lab with uranium and thorium. This is okay. I even have a radionuclide lab where we can use other radionuclides, but we also can use neptunium, so we have access to a hot lab through a collaboration partner, and so we also started to look into neptunium coordination chemistry with those phosphoryl pyrazolones, and of course that's again very important with respect to decontamination aspects and so on and so forth. Why I'm showing you this because again you get very nice coordination complexes. You have 4 ligands around one of the centers, and we can of course also follow the formation again in NMR. Paramagnetic still is not a problem there, and so we also did a lot of interesting exchange experiments to understand the speciation in solution, and also we did the X-sus spectras with the collaboration of our partners. We have access to Grenoble on the beamline, and so you could also look into the solid state layers as a solution by making the corresponding experiments, and so we could confirm really that the solution is really of the solid state. And so this is a very nice approach in order to understand solution solid state chemistry as well, just as an example. Okay, coming back to lithium. So as I said, reverse current, you can use that for separation depending on the corresponding substituents. And so we picked 2 mainly derivatives, like the nitro derivative in the para position is one, which turned out to be quite selective for lithium over sodium and potassium. which was the first paper we published at that time. And we spend a lot of time, so I'm running a bit through because I have some other topics I'd like to show you, to understand really what kind of species are in solution. And you could even use a lot of different techniques to understand, is there a trinuclear, dinuclear, the interconversion between a di and trinuclear, depending on the amount of ligand, depending on the stoichiometries and on the concentration. And you could use a lot of different kind of techniques in order to really show that these phosphoryl pyrazolones are highly selective toward lithium. And again, here just a synthesis, which is very much related to the one we saw before. The yields are okay. And what's now interesting, this position here is protonated, and we can deprotonate. We made the corresponding ammonium salts. And what turned out to be is quite interesting, that these OO distance really depends particularly on the substituent here in the C7 position. If it's a methyl or isopropyl or a phenyl group, you can alter the bind angle significantly. And that becomes really interesting. You see the results here for the coordination of lithium. And so what we also needed to do most of the time in the extraction studies, you need to have a co-ligand. And we also could see that the co-ligand is quite influential in the coordination of these corresponding cations or lithium together. So we have a dimer, a different kind of dimer with solvent, with a co-ligand. This is like a phosphorus ester, very typically used in extraction studies. We even have a combination of both, and we even have a trimeric, trinuclear compound, which again is here phosphate oxide, phosphine oxide on top of it, yeah, which also coordinates. So I think it's one of the first crystal structure where you see the corresponding extractive species, which you can then extract out of the aqueous phase into the organic phase to separate from potassium and from sodium. And so we have a lot of different kind of techniques. We looked into NMR speciation studies. I'm not going to go into my detail. I refer to the paper if you're interested in this. We also looked into corresponding liquid extraction and solid liquid extraction, meaning you have just a salt or a solid material, and you just add the ligand in an organic solvent, and then you selectively only extract the lithium, and everything else remains in the solid state. And so with this, you see this is lithium, and you see the other ones like sodium, potassium, and even cesium, and there's almost no extraction in the SSL or in the liquid extraction. Now that continued in one paper, also not going to go into detail, and when we realized this, we changed a little bit the position. We changed the NO2 group by a CF3 group. And what happened now is that it became selective by pH. So cutting a long story short, the one you've seen before, we can separate now from the alkali metals. But what is more important, if you look into brines, they typically are also associated with magnesium and calcium. Now, if you go to the Atacama desert, for example, and you want to use those brines which they recover there, you have a lot of calcium and magnesium. So what you're going to do, you make it as caustic as possible in order to separate magnesium hydroxide and calcium hydroxide. This is very expensive. You have to recrystallize, you have to purify. You need the sun for a long time to dry out, to crystallize in the end your lithium, and then you separate it in the end as lithium carbonate. As I said, it takes up to 24 months. The brines are typically slightly lower acidic, yeah? So they are not really basic because you have magnesium and calcium in there, or else it would be separated automatically. So you start already with a more acidic brine. Now what we can do is, we can now selectively, by adjusting the pH, at low pH, our ligand is selective for calcium. So at a pH around 1 to 2, you only take out calcium ions. So calcium is separated. Then you adjust between 3 and 4, it becomes selective for magnesium, and then lithium remains, and then at about neutral pH you select then corresponding the lithium. And so we've done this on the cover. You have here the pH, so it's like, you know, these little machines where you put a coin and then you maneuver and then you get the iPhone, or you get the 100,000 bill or whatever, or you get just like a puppy out of cotton, or nothing. And so here you really adjust what's going to be taken out by adjusting the corresponding pH. I think that was very fascinating for us, because now you can much more sustainable without adjusting too high the pH, being selective for lithium. And that's a much, much better, in our opinion, interesting approach towards the separation and recovery for lithium. So we're going to leave lithium and the recover earth metal, go to the second topic. P4. P chemistry, polyphosphorus chemistry. To understand the build-up and the cut-down of PP bonds is quite complicated. And over the last, I would say, 15, 20 years, since I'm really academic active, I'm being fascinated by this subject. I don't know why. You know, sometimes you see somebody and you know this is just, yeah, for me it's not a human, for me it's the element. I saw phosphorus and I was addicted to it. So I can't change it. It's for me the thing. Though, and since many times, many years, also together with a very good collaboration partner, we did the habilitation together in Münster at that time. We really looking into P chemistry in every aspect. And we started really in the more problematic way of looking at P chemistry. You need glass boxes, Schlenk lines, toxic solvents to understand that chemistry. Because phosphorus, and you may or may not know, is a very pyrophoric. Most of the low coordinated in low oxidation state phosphorus compounds are extremely reactive. Many of them really toxic, and so it is, in some instinct or in some respects, it's really difficult to work with. But that motivated us over the time to understand how we can maybe rethink phosphorus chemistry. And at the very end of the talk, I will show you an alternative, which is for us very important. So what we're trying to do over the years is make new kind of precursors, motivation you will see in a moment, new kind of PN heterocycles, because they are quite interesting. If you have like 2D materials and you change phosphorus, nitrogen by phosphorus, for example, you change the electronic properties. And very interesting photoluminescent materials derived out of this. So we're starting also to make new kind of LEDs, which contains phosphorus. Don't get mistaken by a phosphor, that's just something else, but really the element phosphorus is those materials, and they make quite promising new applications. So we just recently published, for example, an phosphor which has like room temperature phosphorescence, which is quite something. And so this is where it is beneficial to develop new synthesis when being able to make compounds which have phosphorus instead of nitrogen, which is not that simple, to be honest. Then we have the concept of metathesis. You know, all CC bond metathesis in organic chemistry. In inorganic chemistry, people would say, oh, there's scrambling reaction going on. So a scrambling reaction is nothing else than a bond metathesis reaction. And now if you understand bond metathesis with heteroatoms, you can use it synthetically. And so that is for us a motivation, was for us a motivation for a long time, to really look into bond metathesis, because it gives you a really, really nice compound. Again, that would be a different thing. And then of course P4 chemistry. Now if you want to build up PP bonds, there are concepts. Now what you saw, we have complex PP bondings, and why is it interesting? Because those cyclophosphanes is just compared to organic chemistry some motivation. We have catenation in organic chemistry, so what about catenation in inorganic chemistry? Yeah, instead. And often people say phosphorus is the smaller brother of carbon, or the phosphorus is the carbon copy. It is true in some respect with low coordinate phosphorus. And so there are ways to catenate those bonds. We've been maybe quite known for putting cationic ligands on a phosphorus. That's our motivation, something like an imidazole, for example, you see here. So our question now, and I'm going to go to pH compounds, was at some time, how do we build those catenated polyphosphates? And the intermediate is proposed to be a phosphinidine. Phosphinidine are really highly reactive species. You cannot really separate them. You can put a metal on them, then you can prove that you can make a metal phosphinidine. If you don't have a metal, they normally oligomerize. It gives you either diphosphine or they give you cyclophosphine of different ring sizes, depending on the substitution pattern. Now, what if we just change a typical R, which could be an alkyl or a phenyl group, by a cationic group? So the motivation was, can we make the very same compounds, but just placing around these cyclophosphines an imidazole? So that would give us, in the case of a 4-membered ring, a tetracation. So a tetracationic compound. It's very similar to this one, except that the cyclohexyl group has been displaced by an imidazolium group. And now, why? We could prove that we can make the tri-membered and the 4-membered one, and so this chemistry is really very much related to this one. And again, the motivation for that is because phosphinidine and phosphinidine chemistry gives you also ligand, which can be used in catalysis and so on and so forth, and some other material chemistry science. Now, if you look at these tetracation, it becomes quite interesting because the P core here is very electron deficient, meaning you can really react it with a nucleophile. And the nucleophile would attack somewhere on the phosphorus. So if this is the case, we could think of using those tetracations as a phosphinidine transfer reagent, but not with a phenyl or alkyl or aromatic group, but with a cationic group. So this is the motivation from a lot of people working on those phosphinidines. As I said, there's like Weigand, Cummins, Herein, and they're using them in catalysis and so forth. And they're using those polyphosphanes as a phosphinidine transfer under certain circumstances. So we've just tried, okay, what if we react this tetracation with a strong nucleophile, such as a phosphine or even a carbene? That's a different point. And what can we do with these kind of compounds? And it turned out to be extremely versatile. We can use these tetracations as building blocks. And now I'd like to pay you one very important attention, always about these LCPs. So this is the imidazole, and this is a phosphinidine unit. And this is stabilized by, in that case, a phosphonium unit. Now, depending on the nucleophile, there are three different types, like a phosphite, or a phosphine, or a phosphide with trimethylsilyl group. So that chemistry I won't talk today about. I'd like to focus here only on this one. So if that works, you should get a PP here with oxygen, silyl oxygen bonds. You know, trimethylsilyl oxygen can be cleaved. So you see maybe quite reactivity patterns here. We have also a reactive PP bond. And also we realized in our chemistry that a imidazolium P bond can also be broken. We can also, with certain approaches, cleave a carbon phosphorus bond, which is normally not that easy. That's a different topic. So that compound, and let's explore this one because this is really fascinating in my opinion. Now you take the tetracation, you react it with these silylated phosphite, and then you make exactly more or less quantitative this compound. Now again, you have the imidazolium here, the cationic group. You have a phosphanide and a phosphonium. So you have a phosphonium phosphanide. Now that's a very simple molecule. But if you look at this, it's a cation. And we have reactive silica-oxygen bonds, which you can hydrolyze by just maybe using an alcohol to make the silyl ether and maybe protonate on that one. And you can do this. Or you can use fluoride, whatever, or another nucleophile, and you can selectively mono-desilylate one of the oxygen. Make the neutral compound, and then it coordinates even with the sodium triflate, which you get from this reaction, so you get array coordination chemistry. Phosphorus oxygen bonds are very nice in coordination chemistry. This is the NMR, that's a 3 times silylated version, monosilylated version, cation versus the neutral one. And why I'm showing you this, because you can see that you have 2 different bonding environments on the phosphorus. So you would expect in the phosphorus A system an A-B spin system represented by a doublet, 2 doublets. That is important for one little thing I show you in a moment. Okay, that's the molecular structure of the disilylated version, and that's the molecular structure of the sodium triflate. Now you can protonate and completely desilylate, and why is that interesting? Because first of all, you can teach student deuterated experiments on complicated systems. The NMR becomes quite complicated, everything understandable. You can make crystal structure coordination as well. So you see something completely desilylated, PO3 unit. Yeah, you can even have the monosilylated, you see the corresponding tautomer, because you can either protonate here or you can protonate on oxygen, so you have also tautomerism, which again teaches a lot of stuff. Now why I'm showing you this is a very important next step. You can take the completely protonated version, you can even protonate that one. Now what's so funny about it? This is nothing else if you consider that part of the molecule as an OH unit as a protonated phosphoric acid. So that means that part here is nothing else than a imidazolium phosphorus transfer reagent, and as a side product we would just liberate phosphoric acid. How can we prove this? Very simple, by the reaction with water. So if you take the compound, react it with water, you get the phosphine, the cationic imidazolium substituted phosphine, and you get phosphoric acid. Okay, now it becomes interesting. We can selectively cleave also the PP bond and can use these compounds as an imidazole P transfer reagent, which is very simple, with very simple chemistry. First look at the coordination chemistry. So we've done this with copper chloride. Again, you can use a halogenide to cleave the silica, trimethyl silica, building the trimethyl silica chlorine bond. And you make coordination complex. You make a copper 6 core. You make in the case of copper and silver, you make these tetranuclear complexes. But be aware that we still have these PP bonds. We have not yet cleaved the PP bond because we just stopped at the first desylation step. Gold also makes more or less the same, but you see a very funny thing when you see already metal-metal bonds. So this is already a gold 4. Can we prove this further? We can use these compounds, and we now take the one which you've seen before, and it's to react it with gold halogenides or copper halogenides. And what we found out, again from a more theoretical point of view of interest, that the structures you derive are dependent of the anion. Let's look at the copper ones. Yeah? So in the case of copper chloride, we get a tetrahedral copper core, where the copper-copper bond modules are bridged by a chloride. If you go to the bromide, we see that the distortion, the tetrahedral starts to be bent already towards the square planar one. And if you get the iodide one, we get the square planar copper, and we have the iodide on top of it, which is quite interesting. You will see in an example in a moment again. Now, and the most important one, that's the silver you've seen before. We still have 2 silyl groups, and we said we can take them off, for example, as alcohol, or with water, as we've done it before. Now, if you do that reaction, and you know, if we have the PP bond, we would expect in the NMR, our AB spin system, the 2 doubles. Now, if you plunge in that compound, methanol, you get a very weird NMR. It's just a singlet. And you get super big crystals, quantitative models. So the question is, what is this? Yeah? It obviously has only one species of phosphorus. And remember from the hydrolysis with water before, it must be something like an imidazolium P. Because in the solution, because there were the redissolved crystals, the solution contained another phosphorus. It turned out to be a silver cluster. Yeah? So now, guide you through this silver cluster a bit in more detail. You can make this, by the way, directly from scratch. You start with a tetracation, you use a silylated phosphide, you get this compound as an intermediate, you plunge in silver triflate in methanol, and you make this one more or less quantitative. I draw your attention also on this yield. More or less the whole batch is quantitative. You make it on grams. You can make 100 grams of it if you want to. And our clusters typically are separate 5 milligrams after long separation times, and here we make it quantitative. Now, how is it built? We have 12 atoms in an FCC arranged, and then, this is an octahedral, sorry, and then on the quartz planar of the silver on top is one of the phosphorus, and the phosphorus carries, of course, then the imidazolium ones here. And so, 6 of the corresponding silver atoms are coordinatively saturated by the triflate. You see the seal triflate, and that gives you a cationic silver cluster of the all-over formula silver 12. LCP, our phosphinidine, which carries the negative charge, one of them. It's balanced by the positive charge of this one, so this is neutral, but 6 of the silver are formally cationic, so you need 6 triflate to all overcharge, balance the whole complex. Now, why is this interesting? Now you can also use different counteranions for the tosylate, for example. You don't use the triflate salt, or you can even use the silver oxide. And then the counteranion would be your phosphoric acid anion, which also coordinates to your phosphorus. Now, since I'm also affiliated with South Africa, I'm an extraordinary professor in Stellenbosch, I have close contact with Len Barber, who is a physical chemist who's doing absorption experiments. So I took some of our samples down there because I was quite fascinated when I looked at the crystal structure, because that's the crystal structure of these molecular silver cluster. And what we realized that it crystallizes from dichloromycin as a solvate. And so the solvate is quite interesting because if you put the solvate, beautiful crystals, into the DSC, you see here the DSC, it loses quantitative all the solvent. So at a decent temperature, 100, 130 degrees is enough, and all the solvate is gone. Now, when we took and investigated these clusters, again, by the way, they are quite air stable, which is also unexpected. For a couple of hours to days, you can keep them on air, not too unstable. Then you look at the material, and it's still crystalline. So what you do at that moment is, of course, okay, well, we can make the crystal structure of the solvate. Can we also measure the crystal structure of the crystals after DSC? This is a solid state transformation. So we put the crystal on and we realized that we can get a very nice crystal structure with one difference. It's a different Raumgruppe, in English, tiny point group, not space group. Sorry, sometimes I'm missing words. A different space group. The only difference is that one of the tosylate is being rotated by 90 degrees. Not like this. Now, working together with Len, he is a specialist on putting in porous materials gases. So we looked into gas absorption, and quite interesting is this is the activated structure after DSC when we take out all the DCM, and then you see a very small voids. So you see the tosylate is like this here, yeah? So then when we pressure CO2 at 40 degrees, this tosylate opens or rotates by 90 degrees and the voids become quite big. So we change the void by a factor of 3. And the void is filled with approximately 2 CO2 molecules. And then what we can do, we can take again the CO2 out and then the tosylate goes back. So we have some kind of a pressure-induced gating system in the solid state. And it is reversible. So we put the structure, put it back forth, and we always come to exactly the same result on the diffractometer on a single crystal. So you see what happens. It's like a gating system which we find quite interesting. And so you see that the structure before and after, really they match. Yeah? So that really is a solid state transformation, which I find quite interesting. And we know those processes also in nature, that you have some function where you can have kind of a gate system. And of course, we've done this also, with ethylene, for example. It's not that nice, but it also has a bit distortion here. But it also comes back to the same result that we also can gate for ethylene. And that is, of course, quite interesting also for gas separation. We're looking into this. And even more because we have our own catalysis stands. And we're trying to look into hydrogenation of acetylenes, for example. We're also looking into, as I said, ethanol, methanol conversion. And so for us, it's quite interesting to use those compounds, particularly also silver, for like ethylene oxidation, ethane oxidation to ethylene oxide, for example, is done on a silver catalyst. And if you can drop the temperature by 100 degrees, the process would be much, much more sustainable. And those clusters actually offer something like this. Because if you look also at the structure itself, I told you that the remaining triflate coordinates to 6 silver atoms. So we have silver atoms which are not coordinated. They are free. Now what if you add a coordinating solvent there? For example, acetonitrile. Then you can actually place acetonitrile on the non-coordinated silver atoms. Now you can of course think of other ligands. You could exchange maybe the acetonitrile by a bidentate ligand or tridentate ligand and so on and so forth. And we've done this of course. Now if you now react first of all, this one, for example, acetonitrile or dichloromethane, it depends a little bit on what kind of solvent, polarity, reaction conditions. Again, you get beautiful crystals, and in the case of acetonitrile, we get like one-dimensional strands. Now this is a 1D MOF, with the difference that the linker is not a single atom or a POM, which is being used, it's a metal cluster. In my opinion, I think it's the first example of a metal cluster being used as a node in MOFs. If you do it in dichloromethane, interestingly, we get like a wobbly coordination, which is, I think, also quite interesting. And if you look at that structure here, we even see that we have 1D chains with a discrete molecular clusters. So they alternate. So you even can construct different kind of clusters there as well. Now we've done 0D, the molecular version. We've done a 1D. What about 2D and 3D? Now, of course, you need to have a different linker. So we've done ditopic ones, for example, carboxylate, which gives you more or less like a planar. And that is prone to give you 2D. And this is a molecular structure. There is no simulation, nothing. It's really the crystal structure. And of course, if you go here, tetrahedral, you would make the 3D, and that works quite nicely. And this is the 3D coordination polymer, which has the corresponding silver cluster as the nodes for your corresponding coordination. Now I said the halogenides are for the architecture quite important. So if you take the cluster and you change over the halogenides, what we can do, we can now expand. So these clusters are in solution, they are mobile. And we can show this also by NMR in a moment. So depending of our starting cluster, if you use iodine, bromide, or chloride, we make a silver 20. And these extended clusters are quite beautiful. And they have a little bit of a difference, the iodine versus the chlorine and bromides, just by the alternating of the corresponding halogenides on your clusters. Now, why is that interesting? Because that is something which we may know from the photo process, to make photos, to make silver nanoparticles. And these are now silver halogenides, and really growing an interconversion of those halogenides, which explains much more even our old photograph process. For the younger generation, which use a digital phone, it's not important anymore. The older version, which I consider myself being, and I used to work in a laboratory to develop old pictures. So this is for me actually very something funny that we actually really look into the formation of nano silver clusters. And we can learn about the different alternation and coordination, and then there's like 3-4-3 versus 3-3-4. So it's just a difference where the halogenides actually saturate. And we can, last part before I come to the last part of my talk, you can see particularly the iodine ones at higher temperature, the NMR signal becomes a singlet, meaning that these clusters are wobbly in solution. So there is much, much more to gain by adjusting the reaction conditions, and we have already identified that we can even make a silver 26 cluster. And for this cluster chemistry, people would of course ask, what about copper and gold? And of course we've done the copper as well. Copper is more difficult than gold, silver, unfortunately. The yields are not that good, but we can do it, but they are fluorescent. So the copper clusters show fluorescent materials, and with gold we only manage at the moment, unfortunately, to make a gold 6, but that's also beautiful. And then again you see also interest in the mass spectrum for those ones who like phosphorus anymore. There's an A to A prime, X, X prime, A, X double prime, X triple prime spin system for those ones who like to look into this. Okay, last part. P4, I said, activation. We have in Germany a huge problem with white phosphorus. You know all the allotropes, this is first semester main group chemistry, I hope you remember. Even there was a Nobel Prize on the exfoliation of graphene, phosphorine, and so on and so forth. Interesting material. People like to have graphene and phosphorine type materials because of electronic properties being used in electronic application and so on and so forth. Now, but where does the name come from? And I think you maybe have seen this picture. This is a discovery of phosphorus by Henning Brandt, and also Wright of Derby made this picture because he showed the moment where Henning Brandt, 1669, discovered phosphorus. Yeah? And phosphorus comes from phos, light, and phoros, bearer, so light bearer. And you see exactly that situation. So we need to understand Henning Brandt. Why did he do it? He was looking for the philosopher's stone. You know the philosopher's stone, you know from Harry Potter or something like this. If you touch something, it converts an element of different things into gold. Why was Henning Brandt so in need of gold? Because he was married to a very rich pharmacist. She had a pharmacy. And he was using all of her money. So they got almost bankrupt. And so he got in jeopardy because of course, he didn't want to tell his wife that he spent all her money. So he was looking for the philosopher's stone in order to make money, gold. So what he did, very stupid idea, why would somebody do this? He used urine, so this is a little bit of one, boiled it, got a syrup, and then, of course, our urine actually contains phosphate because we excrete as mammals our phosphorus primarily via urine and not via the solid material. So most of our phosphorus is in the urine. Do you know how much do we excrete every day by person? What do you think? Each of us sitting here, what do you think we excrete every day? Why is that important to know? I will tell you in a moment. What do you think? 5%. Do it in masses. From 5% of what do you think? Milligrams, grams, kilograms?
Milligrams.
Milligrams. So like 5 milligrams, 10 milligrams. Who gives more? Who gives less?
10 milligrams.
10 milligrams. More or less? Up to 1.5 grams a day. Now, imagine, all of us sitting here, peeing every day 1.5 grams by maybe 25, 30 people.
Now, how many Argentinians are there in Argentina?
45.
45 million. So 45 million Argentinians, P 1.5 grams, plus 1 German today. So, and do you know where it goes? It goes into the wastewater stream. And what happens with the wastewater stream? It goes into the biggest river, which I learned today. Widest. And maybe biggest, I don't know. It depends on where you could look at the bed. I know this is not a joke between the two of us. Because he said, I didn't believe it. I was like, yes, I was acknowledging it, was very happy that they have the widest river. Anyway, so it goes into the sea. Mankind is not able to recover most of the elements out of the sea. There's a lot of gold in the sea, by the way. No problem, we would be extremely rich, but technology is not there. The same as phosphate. Only algae, with algae blooming, of 100,000 millions of years, are able to deposit a lot of phosphorus, where we actually got our phosphorus deposits long time ago. So we cannot do this. But we spend it every day into the switch. And that gives us a lot of problems. Why? And now comes a very interesting hypothesis. And for the lecturers, I'm not allowed to answer. But for the students, yeah, to make it a little bit interactive, I have a prize to give the right answer. And the prize is Haribo. You're not allowed to answer, and I know you love Haribo too. And that's what River Sport. Anyway, so why is phosphorus the element of life? Who can answer that? Energy. So, you're a lecturer, but I don't mind. It's fine if you share with everybody. No, it's fine. No. But that's not. What would you consider the element of life? Here we have some phosphorylation. So, but what are the elements? What would you consider the 5 elements of life? I help you. Carbon, oxygen, nitrogen, and phosphorus. And out of these 5 elements, my hypothesis is only P4 is the element of life. I don't care about carbon, oxygen, hydrogen. Because even your energy systems have oxygen, nitrogen, carbon, and hydrogen, and a phosphorus. So what makes the other elements then different? So it's obviously not the biological related molecules. Must be something else. And who can answer that question gets the Haribos. That should be a good motivation, by the way. Unfortunately,
Maybe because
I can also do it outside, people don't get it.
because of the structure of ATP.
No, because the structure is also determined by the other elements as well. Yeah. So it's not the organic molecules by itself. Think about where do we get the organic, and then you may be on the right path.
Isn't it for the DNA and the nucleic acid important?
There is also carbon, hydrogen, oxygen, nitrogen.
Iron.
Well, we talk about the most important ones. Yeah? So we don't talk about the transition metals and a little bit of salts, selenium and magnesium and sulfur.
Bones.
Huh?
Bones.
Bones, calcium, but again, yeah, that would be construction, but you could also live, there are living forms which have no bones, like a snail, a prune, no. How do you make biomolecules? I'll give you one example and maybe you get an idea. Sugar. How do you make sugar? Students here, or PhD students, or whatever consider himself as not being a professor. Huh?
The process is photosynthesis.
Yeah.
That's what you mean.
Yeah, sugar. How do you make sugar in nature?
And you need like a fat cell, you need light, and you need oxygen.
Yeah, what else?
Well, the carbon dioxide.
CO2 and? Water. Okay, so CO2 and water. So you have carbon, oxygen, hydrogen. These 3 elements. Where do you get CO2 and water from a plant?
CO2 from water,
Yeah.
water from the soil, CO2 from the air. Or, well, depends
What?
on the plant.
Okay, so we're gonna go in the right direction. Now, what else do you get from the air? Which other element?
The minerals, like phosphorus.
No, what else do you get from the air?
Oh, sorry.
From the 4, we have like carbon, oxygen, hydrogen, we and the next one? Nitrogen.
Oh, yeah.
So, that's the answer. And you got it. You can share, you can take it home. So, unlike, and you talk about, and you talk to me, and you were explaining me how to make sugar. So that's the answer. Unlike other major elements of life, CHO and N, phosphorus does not have a gas phase and cannot circulate freely in the atmosphere, which has very important implications with respect to phosphorus recovery and reuse. That means if we don't have phosphorus, we cannot live. If we spend it, we cannot live. Because now you make those molecules, of course. because they are responsible for the energy, ATP for example. By the way, do you know how much ATP your body produces in mass a day? What do you think? Yeah, do you know how much?
No.
What do you think? 5 grams? 10?
10.
10 grams. Who says more than less? You like the tens. Who says more or less? Who's for more? Okay? Okay? More. Your body weight is produced approximately a day ATP in order to get your energy. Your weight of your body creates ATP, not at the same time, but if you count the masses of ATP being produced, it's about your body weight every day.
Every day.
Every day. That's quite a bit of one thing. Huh? There's a lot of phosphorus involved, by the way. Okay, so this is some geological stuff, how we get phosphorus into the plant, which is also very important to understand. These are different pathways. And so if you're going to go to the point, maybe one last sentence here, you think you can make good the loss with phosphate rocks, but what will you do when the deposits are exhausted? Well, then only 200 years and they'll be finished. You think we are progressive because we're living on our capital, phosphate, coal, petrol, literally squander them all, that's your policy. That's a book 1928 already saying that we cannot dispose it. And if you look at this one, Earth has a lot of phosphate. We will never get rid of it because there is no process in order to remove phosphate. We are very good in distributing it very finely. This is a really big problem because from all the phosphate, 4 by 10 to the power of 15 tons phosphate or phosphorus on Earth, that little bit is only available for feeding to produce food and feeding us. And what we're doing we're going to put it into wastewater, we put it into the sea, and we cannot recover. So there's of course a problem. I'm not sure if really the 30s is the problem. Now we have phosphate definitely in the last 600 years, but it's something our society needs to deal with. And so now, last part, promise, we've got a few slides, but these are the cool ones. So this is how you separate phosphate from as an ore. So this is like Lao Cai, the Vietnamese mine, which I visited some time ago because I collaborate with Asia quite a bit. So this is high purity apatite, which normally then is of course converted in the most important acid, phosphoric acid, for the production of fertilizers. But at the same time, humans are very strange, because this stuff also needs to be used for making PCl3, which is made via P4. So what we're doing is normally, we use of course the phosphoric acid in order to make fertilizers. Comes the first big problem, which people don't really look into. Phosphoric acid, why is it cheap? Because it's connected to another very important acid. This is the sulfuric acid. And the sulfuric acid is the cheapest ever produced acid. And why? Why is also sulfuric acid going to be a problem in the future? Because, well, you separate calcium phosphide when you react calcium phosphide with sulfuric acid, making calcium sulfide, and you liberate phosphoric acid. First semester fundamental undergraduate laboratory courses. And so everybody's using phosphoric acid. Why? Why do we have so much sulfuric acid? Why is it so cheap? And so you never can only think linear. You always have to be left and right. And this is also the next problem. Sulfur. Why would sulfur be a problem? We have so much of it. Where does sulfur come from for making sulfuric acid? From oil. From oil. Yeah, so what happens? 80% of the world's sulfuric acid is byproduct of the fossil-free production, cutting back on oil coal, and the natural gas means producing less sulfuric acid. That's important. The sulfuric acid is critical to make fertilizers as well as green technology like solar panels and batteries. Chemistry also depends on fossil fuel resources. You can talk about not producing oil anymore, but at the same time you can even make fertilizers. So if we don't produce oil, we cannot make fertilizers, we cannot feed us. You know, these chains, they're not openly communicated, but this is what actually needs to be done. Now, and then what we're doing, this is the process, going back. What we're doing, if we go and use most of the P4 for industrial use, so most of the platform chemicals enter via P4 chemistry, meaning very nasty processes. You need to reduce, and now the stupid thing comes. You go from the oxidation state +5 to elemental phosphorus, in the end reoxidize to make phosphorus 5 compounds, where phosphorus again is in the oxidation state 5. So mankind, and that's maybe also a lesson for students maybe, is stupid enough. We do have some other bio-related people that are doing differently. So mostly chemistry relies on thermodynamics and not on entropy. Entropy is much better. The processes are much greener. But what was human doing? Thermodynamics. Putting 5 electrons in and out, this is really energy demanding. So why would we do this? Because we need these compounds to make these red drugs, like PCl3, PSCl3, POCl3, PCl5, and phosphinic acid, and so on. And these what we need every day: flame retardant, chlorination, battery electrolyte, herbicides, pesticides, catalyst, ligands, vitamin A synthesis, fumigation, extract reagent, plastic additives. That's our daily life. And people don't really know that this is heavily based on P4 chemistry. And now come back to us. If we don't have P4 in Europe, we can make that stuff. And again, these P4 chemistry relies on chlorine-based synthesis, multi-step synthesis, toxic reagent, no P recovery, and a lot of waste. And what we're making, 2 very important compounds which have no value as being an intermediate for making these compounds, only required for the synthesis of P chemicals. Fundamental chemistry in PCl3 and P4 is nice, beautiful, we love it. Fundamentally, we do a lot of chemistry, but industrially, it's a nightmare. Now, P in synthesis, why do we need it? Again, a Bursov reaction for the organic chemists, Staudinger reaction for the biochemists, Wittig reaction to make vitamin A, or the Apu reaction to invert the stereogenic center, very simply, conversion of an alkyl halide into hydroxy derivative. Now, or the other way around. Now, P4 production is quite heavily, and these are the compounds we make from P4, but most of them are phosphorus 5 compounds. Yeah? So when we started, we were looking into, is this really the state of the art? Can we continue like this in the future? Do we need to change something? And so we started, first of all, to look into P4 conversion reaction. And I'm not going to go into detail, it would be a talk by itself. So we came up with a plan. So we're looking into white P conversion reactions. Show you one paper, not much. Then P recycling, spent, for example, phosphoric acid of lithium iron phosphate, which I showed you before. You can recover from lithium iron phosphate again phosphoric acid, which then you can make fertilizers or again batteries out of it. That's a cool thing. And this is like secondary resource. It comes from our waste and not from our grounds, not primary. Then phosphate conversion, this is a highlight, which I will end up the talk. And redox transition is something for the future when I come back. Maybe eventually. So, first thing, P4 conversion, cut the long story short, you can read our Nature Chemistry paper on that, where we can directly convert P4 and make POP and PC bond via a transfer reagent, which we have a new kind of synthesis which does not rely on chlorine-based chemistry. And so it bypasses PCl3 chemistry. That has been published some time ago, and we learned in this process is something very interesting, that we actually can also alternate phosphate, cleave directly phosphorus oxygen layers. Now, phosphates, where do we get them? So first of all, you need to make an analysis, what waste you can use to convert into phosphoric acid, and then use the phosphoric acid to make phosphorus 5 compounds. That would completely bypass primary resources, because we can use our P, or our battery recycled material, or our flame retardant out of polyester. You know how much flame retardant one of those ester polyesters here is? What do you think? This is like these triethylphosphine oxides sometimes, or in the construction when you put the walls, there's like these foams. There's up to 20% of a flame retardant based on either these exolite, which is an diethylphosphonate, or on this triethylphosphine ester. You sit on that. You sit on up to 20% flame retardant in your car, on this and that. And this is not being recycled at all. Again, we don't pee it, we also sit on it, and then we just burn it in the air. So there are a lot of alternative value chains which you can look into. And again, if you look something like this and you find in your IP or in your research something like this and you convert it, you can make money out of it and you can save the world. Isn't that incredible? So we came up with a very nice way, waste to treasure. I showed you this already before, where we're actually also looking into the recycling of the phosphoric acid. So this phosphoric acid we gain here from our lithium iron phosphate recycling, we can use to make phosphate conversion. So we don't need primary resources. We use the old vehicle, took the battery out, take the cathode, and we make out of the cathode a pharmaceutical. Isn't that nice? So how we do this? Again, cut the long story short. different kind of primary, secondary phosphate resources. Could be phosphoric acid, apatites, pruite, lithium iron phosphate, or even triacyl phosphate, which I showed you as a flame retardant. You sit on it right now. And with a very nice recycling process, we convert it in a P5 transfer reagent. So what we've done is nothing else than converting a phosphorus 5, oxidation 5, in a transfer reagent, which is also oxidation state 5. So we do not change the oxidation state. How we do this? Very simple. This is a phosphate. We add triflic anhydride with a ligand, and that combination, that would be a talk, we don't have time for this, can selectively cleave 2 oxygen bonds and implement a pyridine ligand. So we exchange 2 PO bonds by 2 PN bonds. Now coming back to fundamental chemistry, PN bonds are very labile, being used in pharmaceutical and biochemistry. Christian Hackenberger is doing a lot of that chemistry. So and then you can react this with a nucleophile, and then you have a base. The pyridine can deprotonate, act as a base in situ, and you implement, for example, an oxygen phosphorus or an oxygen nitrogen bond again. And with this, you can make a lot of different kind of halides molecules, a chiral catalyst, just by reacting this compound with the alcohol. And I restrained here only to talk about homo substitution. I would have had a different talk also on C nucleophiles, but that would be another hour, and I don't want to bother with this. So meaning, you can even make modified biomolecules. This is like an HIV agent, for example. You can even make lipids, phospholipids, very simple with this. You can make different kind of transfer nitrogen substituted phosphorus 5 compounds. We patent this. Currently we are ongoing also to a TCP patent on that one in order to really have a different phosphorylating agent. And now we're collaborating also with a lot of biochemists, material chemistry, and using to use those ones. And of course the next generation is also not altering just 2 oxygen bonds, maybe 3, maybe 4. Then couple it with a redox process so that we can go also to phosphorus 3. Because some phosphorus 3 compounds are important as ligands, catalysis for example. But then we would go phosphorus 5 plus 2 electrons, phosphorus 3. We would not go phosphorus 5 plus 5 electrons, elemental phosphorus and reoxidase. Okay, with this, we are in the last stage. So this is what I talked about. Now we're looking into phosphate electrochemical synthesis to alter also the oxidation state. And as I said, this is then maybe something I can maybe talk about next time. Thanks again for the invitation, and I hope I didn't bother too much. There's a lot of different things, and of course I have some collaboration partner worldwide. And yeah, keeping the time, as I said, is exactly 1 hour, and I thank you very much for your attention.
Tenemos un tiempo para preguntas y se anima.
I have a small question. When you catch the lithium or other cations from the nature, which is the efficiency?
You mean the extraction? Oh, we have the efficiency goes sometimes up to 90-95%.
Yes.
Yes. And with solvent extraction is a bit complicated because you need to know the corresponding equilibrium rates. But we do have very selective extraction, even up sometimes more than 100%, because we can capture sometimes even 2 lithiums at the same time. That's a different generation, I didn't talk about that. And we also have the possibility not only to catch the lithium, but we also can catch the hexafluorophosphate. And then we also have like rates up to more than 100%.
And you have your molecules that are these very nice molecules are in solution, or you can, it's better to fix to a substrate and
this is the next generation we're doing right now. We're talking like an ion exchange, like on a solid support. People have done this with phosphines to capture gold and PGMs, for example, and then they captured fully loaded capsule being burned, and then you can recover your metals. We'd like to, as you see, depending on the pH, to wash it away again. And so yeah, at the moment we're trying to have a polymerization, like a monomer which you can polymerize in order to also put it on a solid state. And then you just wash here material through, and then it captures only, for example. But that's technologies which are. You can even think about what we're also doing. I didn't show that, membrane technology, and also be building our own electro-oxidation, also with our phosphate ligands type partly, and then you can also do an oxidation of your cation, for example, cerium. You oxidize it to cerium-4, and then it becomes very selective only for cerium, and lanthanum is not being, or the other rare earth metal is not being considered because it's an oxidation date +3. They become harder and smaller than cerium-3, so it's selective for cerium. You can take it out, you extract it, and then reuse it again, electrochemical, and then you have cerium separated. So there are different kinds of possibilities. Either on a solid support, either on liquid solid liquid or liquid liquid. So. And all of these depends on your application later on and your corresponding waste material you're looking into.
In line with this question, when you extract one lithium, you are releasing a proton.
That depends on what kind of extractant you have. You can have an anionic extractant, you can also have a neutral one. So that's the point.
Because if you have an ionic one,
yeah,
you are releasing one proton, and then when you have to release the lithium into a recovery solution, you have to add hydrochloric acid.
For example, or another acid, or a different way. You could also use a different method. You could also not have an anionic ligand. You can have also like a switterionic ligand.
Yeah.
That's a different one.
That's the question.
Yes.
So
we also looking at
can you have a molecule that allows you to extract both cation and anion?
Yes, that's
with
what
the same rate of or percentage of extraction.
That was what I meant before. Lithium hexafluorophosphate.
Yeah.
When we recycle lips, the electrolyte is lithium hexafluorophosphate.
But this is when you are extracting from the battery waste.
For example, yeah.
Can you do that in brine?
Yes. There are also ditopic ligands which capture the lithium and the anion.
So, for example, chloride.
Yeah. But we don't really look into lithium chloride by itself because that's not the big problem. Mm-hmm. But I know where you're going, and a few things I cannot talk about because they are patenting things. But yes, that's of course the most important thing. If we really want to separate lithium from lithium brines, for example. And then you have the corresponding problem with the counter anions, and then you need to look in fluoride, chloride, bromide, iodide. Mm-hmm. So the more complex the anion in your system, your more refined needs to be your ligand system. And so, but we do have they're completely different compounds. They don't look like this. These are different ones. We have ligands which are selective for metal anion combinations. But yeah, that's of course very applicative.
Okay. I have a general question. I mean, you showed us a lot of examples of very complicated compounds that combine in a way a lot of what in chemistry we think about as very different type of bonds. For instance, you always speak about coordination or something like that, but we have metal organic coordination, metal coordination, which sometimes it's kind of a metal bond.
Yeah.
For instance, in
like
the silver clusters or something like that. You also have a lot of ionic interactions there. And also you may have solvents or even physical processes, you may change the structure. And the question is, when you have such a very complicated structure with different types of bonds, in the interface where, for instance, metallic bonds are starting and you have on the other side some kind of other type of bond. At the time of predicting the structure, which type of chemical bond is ruling out the story? Because sometimes one type of chemical bonding should, predominate. If you put together with another type, perhaps this kind of bonding is preferring a tetrahedron, and this other type of bonding is preferring. And you may have the question is if you can predict a structure, even working on very similar compounds, or if it's better to have a new compound and then analyze the structure.
So it's afterwards most easier to finalize and then see what you have and then find a solution for it. That's most of the time, even with the computational chemists like this. The prediction sometimes is more like after to say, oh, why do we get what we get? Sometimes predicting and then you make the compound maybe not that what has been predicted. One example we had shown you is this copper cluster where we got from the tetrahedral with the chloride to the square planar with the iodide. And then you can think about, well, Pearson concept, soft. You can about depolymerization, polymerization, the electron distribution in larger iodine, which is much softer. And so you have like ligand field effects, which you then can again understand by polarization, for example. And those systems we have not calculated yet. So it would be quite interesting to see really if you can predict particularly on those clusters. Cluster chemistry in general is quite interesting, but we also have to be a bit careful with our ones because they are not really like metalloids. You don't have like a neutral silver together with a cationic silver. We have charge balance all over again. So that's in that case quite obvious. There is not really something like we have like a electron precise or not electron precise clusters. And there are of course also rules out for the corresponding existence of certain clusters. For the element bonds, phosphorus, that's quite straightforward. There has been a lot of concepts, which I've been in debate when I was much younger, like in the phase of my habilitation, about 12 years ago. There was a main group chemistry, these coordination, arrows, not arrows. Dunkert's model in transition metal being transferred into coordination modes into main groups. So a lot of people start to have like element modification, like the antimony 2 with 2 carbines. Yeah, and then they just did 2 arrows and had like an SB, double bond SB. And so, and we also had one compound one time where we made like an arrow on something. It was just a copy-paste arrow. At that time it was on a cover on Angewand, and somebody was shooting at me like, oh, this is not like a P42 plus ligand stabilized. So this is, these terms being used nowadays sometimes are misused. So I'm really actually, after being also some time in that business, I really like these concepts and descriptions which we have in UPAC, which are really solid. And I don't want to oversell anymore. So making maybe for a phosphonite. Now you can call, again, people start now to make phosphonite as an arrow. Yeah, it's a phosphonium phosphonite. It's not a phosphinidine stabilized by a ligand. But people sell it like that. And so, and then it really sounds more than it is. The compound by itself is beautiful, but the bonding situation is exactly what we understand as a bonding situation, because even quantum chemistry would predict exactly the polarization, the corresponding distribution of electron density, and so on and so forth. We are good enough at that. So we don't need to add extra. So I think our concepts we have nowadays fulfill most of the description of bondings we have at the moment. And only when really something completely new comes, we need to find a new model. That's nice, and then it's a science paper or a Nature. But that happens that much.
And you teach in this direction?
Well, I have a big debate. Even if you put a phosphate on the board, how do you explain 5 bonds on a phosphate? It's bullshit. Sorry. Yeah. So, but then you can look at the double bond and say, oh yeah, in this excitation you have like an anti-bonding system. Then you need MO theory. But it is wrong to have a phosphate, a double bond to an oxygen, and 3 single bonds. It's just wrong. So all the phosphate representation, particularly in the organic biochemists, it's not okay. And then if you want to teach a student to say, well, why is it shorter in one situation? If I completely deprotonate the phosphoric acid, and you have an unperturbed phosphate in the crystal structure, all PO bonds are the same. Aren't they? They're the same. Only if I change to polarization or coordination, things in the PO becomes different. So, and the simplest way for students in the first and second semester is draw 4 single bonds, make a plus on the phosphorus, then you fulfill the octet rule, because there is no d orbital contribution. There is just none. You can calculate 3%. What is this? Nothing. And so then you say, well, why do you explain that the bond is shorter? Then you can just, it's Coulomb. Higher charge, interaction, short gets more, this is shorter. That's good for the first two semesters. And later on, if you're going to go into more defined bonding situation, you need MO. You need the corresponding models, which then explain further. It's the same with hypercoordination. It's exactly the same situation. PCl5, for example. Make a Lewis structure on PCl5. Yeah, for me it's PCl4 plus, Cl minus. Full stop.
I have a quick question. You show that you can coordinate the lithium,
Yeah.
get it out of a brain, but then is it easy to regenerate and get the lithium back from your
Yeah, so the stripping is most of the time not such a big problem. Because then you have a refined organic solvent with your ligand saturated with your corresponding coordination complex, and depending what you want, you can later on strip. And there is a possibility, and then you still can decide if you want to have lithium chloride, then you strip it with HCl. You can even do like the cold process, you can do it with liquid CO2, then you can make carbonates and stuff like this. So there are a lot of opportunities later on to go in the corresponding salts you want to do. Again, it depends on your brines, depends on your ligand system and on, but that's established chemistry. This is not really something which we need to reinvent new.
¿Tenemos alguna pregunta más? Okay, thank you very much.
Thank you.